So we're going to have a look now at parametric equations, which is chapter 8. And parametric equations, there's nothing really that's new here. It's just kind of like a new language of describing things that we already know about. So there's nothing that's going to like blow your mind. It's just like adjusting some of the things we've already got an understanding about. So I've said here, I've got a graph that says x squared minus y squared equals 5. And typically, with two variables x and y, we can relate the two by a single equation involving just x and y. And this is known as a Cartesian equation, which is named after a French philosopher whose surname was Descartes. And that's where Cartesian comes from. He also came up with coordinates. He was the first person to realize that you could say a point in space could be mapped as a coordinate. And so the line here shows all of the points, x, y, which satisfy the Cartesian equation. So if I looked at any of these particular points on the graph, if I found the x coordinate and the y coordinate, the x coordinate squared, take away the y coordinate squared, would be equal to 5. I know that's kind of obvious, but it's just useful to remind us of what does each point actually mean and how does it relate to the equation. But we're going to be thinking about things in parametric now, which is a new way of expressing equations. So I've said here, however, in mechanics, for example, we might want each of the x and y values to be some function of time, t, as per this example. So instead of relating its x coordinate to the y coordinate, in mechanics where we're interested in where something might be at a particular time, we might want to say that its x coordinate is going to be a function of sine over time, and its y-coordinate would be the time squared. So that at the beginning of the journey, it may be down here, and the x-coordinate is just going to be going back and forth with time, because it's a sine graph, and the y-coordinate, as I'm moving, is going up quicker and quicker, because it's t squared, and we know that t squared will get quicker and quicker. So this would allow us to express the position here as a particle as a vector. And this vector would be that its x position is sine t and its y position is t squared. So this thing that I've written here, that x equals sine t and y equals t squared, which I've written as a vector, these are known as parametric equations because each of the x and y coordinates are defined in terms of some other variable which we call a parameter. That is just the name of this third variable, which is called a parameter. Now, the thing that's weird about these is to get to one of these particular points on this journey, if you imagine this is like a thing that is moving, the way you find its position is you need to know what time it is in order to find out what its x position is and what its y position is. You need to have a third value, the parameter, which you can substitute into those two equations to tell you where it is on the coordinate grid. If I said this point over here, it's not immediately obvious what the value of t is. So t is there, but it's in the background. It's not like this one up here where I could just say, okay, well the x coordinate is 3 point something and the y coordinate is 2 point something. All the information is there on the graph. This one's a bit different. To find the x and y coordinates, I don't know what the t value definitely is. I can work it out, but it's kind of in the background. I kind of see it as though the parameter is the thing that is creating the x and y coordinate, but it's not obvious what it is. It's behind the scenes, okay? And to find the Cartesian form of an equation, well, Cartesian equations only have x and y together. They only have x and y together. And we're going to try and convert these parametric equations into a single Cartesian one. I have this and this. I have x is 2t and y is t squared. This is a Cartesian equation at the moment because the x and y coordinates are in terms of the parameter. Sorry, this is a parametric equation. So I want to get rid of t. How could I eliminate t from these equations? How could I take these two separate equations and put them together? Pardon? I could make t the subject. So the first thing that I would do is I would make t the subject. And I'm going to do it for this first one here so that I get x over 2 equals t. And then I'm going to sub into the other equation. And the other equation is y equals t squared. So y would be equal to x over 2 squared, which is x squared over 4. So the Cartesian equation is y equals 1/4 x squared. So we've just eliminated t. That's all we've done for this bit. Because we've just done functions, we want to think about how domains and range relate to this. So they've told me something. They've told me that the input values for t are between -3 and 3. We're only allowed to put those parts of we're only allowed to substitute those values in. And the domain and range of this function are going to be a bit different. So here we've said if x is some function of t, p is just a different function letter. I could have used f if I wanted to. And if y is qt, a different function of t, if it can be written, if it can be written as f of x, then the domain of f is the range of p, because the domain is the x values, okay? So what we're saying here is what you can possibly get from the x values, according to what t values you can put in, that will determine what the x values are, aka what the domain is. Then the range of f is going to be the range of values that you can get here. Really what I should say, instead of saying range, the outputs that you get from this will be the domain, the outputs you get from this will be the range. So let's have a look at what our first one is going to be for x. We're going to explore that x is equal to 2t and that t is in between -3 and 3. So what possible x values can you get here? Yeah, -6 and 6. The x values that you could get will be between -6 and 6. And that's because if I go from t to 2t, it would be from -6 to 6. And 2t is the same as x. So I can say that the input values are that x is between -6 and 6. So this input value about t is going to tell you what domain you can get and what range you can get. So the range of f is the range of q. Well, what do we think the range is going to be? In other words, what do we think the y values will be? If y is equal to t squared, what possible values for y can we get if we know that t is between -3 and 3? What's the biggest thing that y could be? 9. The biggest thing that y could be is 9. What's the smallest thing that y could be? 0. Because in between -3 and 3 is 0. It's a quadratic. So don't just substitute in the extreme limits here. You have to think, because it's a quadratic, what might be the lowest thing that it can be. So because y is equal to t squared, and again because t is in between 3 and -3, the smallest thing that y can be is 0. But it can't. Can it be equal to 0? It can, because t can be equal to 0. But it has to be less than 9. So the range, I would write like this, is that the range is between 0 and 9. And now I'm going to draw this on... So I'm going to go to Desmos. I think I remember how to type this in. If you want to type in a parametric, you type in like coordinates, and then you type the x coordinate as the parametric equation, which is 2t, and the y coordinate, which is t squared. And you'll notice we've been allowed to decide what the values of t are going to be. So we said it's between -3 and 3. And so look what's happened here. We have actually got a graph that has the correct domain and range that we found out. So if I just go back to this page for a second, we have said that y is in between 0 and 9, which it is. There's 9 up here, and there's 0 down here. And we said that x is between -6 and 6. And if I change what t is allowed to be, I will get different parts of the graph. So, I don't know, let's say I went from -1 to 4. you get like a kind of a partial part of a quadratic, depending on what input values you can get and what output values you can get. And people don't often realize this, because what they've done, what they would do is they would see that you had a quarter x squared, and they would be like, great, the graph is this. But actually the domain being between -6 and 6 and the range between 0 and 9 means that here is -6 and 6 and here's 9. It actually means all of this bit is gone and all of this bit is gone. It doesn't exist in the way that we've defined the function. Okay? You've got to be careful about what's going into this and what's not going into it. Okay, so we have now got to think about some other kinds of Cartesian ones that we've got here. This has got some stuff to do with logs. I know some of you are doing logs with Harry at the moment, but if you're not sure, just listen to how this example is. And when we're doing the practice, you can do the ones without the logs. So we want to find the Cartesian equation of this one that we've got here. And we want to find out what the constant is. It's for the domain. It says that the domain is that x is greater than k, where k is a constant to be found. So previously we said that we would make t the subject. Which one do you think is going to be better to make t the subject? I'd only answer this if you've done the which one? I actually disagree. I actually think the one on the left is going to be easier. And the reason I think the one on the left is going to be easier is because we eventually want our equation to be y equals f of x. And this one already has y equals. So if I can just make t the subject of this one, I've already got y equals, and I'm going to save a lot of time doing the rearranging. Now, to get rid of the logs on both sides, you raise e to the power of it. So I would have e to the power of x equals t plus 3. Because when you do e and ln, they are inverses and they cancel each other out, which is why I'm doing e to the ln of t plus 3 is just t plus 3. And so e to the x minus 3 is equal to t. And then I'm going to come over to this graph, and I can now substitute t in here. So y equals e to the x minus 3 plus 5, which is 1 over e to the power of x plus 2. Okay? So that is our first part of the answer. But it also wants us to find out what the domain is. Now, the domain is found by looking at what they have told us here and deciding which one, x or y, for the domain. No, the domain is x. These are the domain of the function. Whatever input values you can get, it's referring to this as the domain. If it was talking about the range, it's the y values. So we're going to try and use the fact that t is greater than minus 2, and we're going to try and see what that means for this. So if you were to put in minus 2, and you can all do this whether you've understood logs fully yet or not, if t was equal to minus 2, let's just see what x would be equal to. We know it's not allowed to do that, but we're just going to see what it would be. And x would be equal to the ln of minus 2 plus 3, which is ln 1. What is ln 1? It's 0. It's saying what power of e gives you 1, and the power of anything that gives you 1 is 0. So this is 0. That seems to be telling me something about x then. It can't be 0, but it's either going to be bigger than 0 or smaller than 0. I think it's going to be greater than 0 because we know that the log of any number is going to be greater than 0. So by seeing that when t is equal to minus 2, x is equal to 0, if t is greater than minus 2, then x is going to be greater than 0. And you can sketch that on a graph. So if I just show you what I mean here, I'm going to just quickly go to Desmos, and I'm going to type in, ignore the fact I'm saying y equals, it's just for this, ln of x plus 3. Instead of x, it's really t. And I'm saying that t is greater than minus 2. So the only values we can get, it's confusing with all the letters actually. I think this is perhaps not going to be useful. But basically saying that you could, the branch of the blue to the right is always above 0. Hence us saying that x is always greater than 0. But all the letters are a bit different there. So don't, if you're finding that confusing, it's my fault because I've tried to show you and then made it worse. So that means that k is equal to 0 for this particular one. And now we're going to try and write down the range of f of x. This was A, and now we're going to do B. So the range of f of x is going to say, how am I going to use this information in here? And this is where you just kind of need to do a bit of experimenting with the numbers. You need to think to yourself, okay, well, I'm just going to see what happens if t was equal to -2, just like I did over here. And we're doing it with the y section. So if t was equal to -2, let's find out what y is, because remember, y is the range. So if t was equal to -2, what would y be equal to? A third. Good. 1 over -2 plus 5. It would be equal to a third. Now, because we know that t is greater than -2, we just want to find out what happens if we make t bigger than -2. So what about if t is equal to something, I don't know, really big, 100? Or, I don't know, I'm going to do 95 because I'm just going to get a 95 plus 5, and that's kind of easy, okay? So if t is equal to 95, I'm like experimenting and trying out some different values here. Y would be equal to 1 over 100, which is equal to 0.01. What about if I made t huge? What about if I made t the biggest that you can ever think of it? What would y be equal to? It's going to keep getting smaller. Would it ever become 0? It would never become 0. It would never become negative, okay? So if t becomes towards infinity, y is going to go towards 0, but y will still be greater than 0. And sometimes when we write that, you don't need to necessarily know this, but if you're going to say it's going to go towards 0, if you put a little plus by 0, it means it's going to go towards 0, but positive side, okay? That's like uni stuff, so if you don't have to use that. So this tells me we think that the values of the range are going to be between a third and 0. So for the range here, I'm going to say that it's definitely going to be greater than 0 because it can't be equal to 0. Was it allowed to be equal to a third? No, because do you remember we said if t was -2, but t has actually got to be bigger than -2, so I won't be adding in an extra line that I've got there, okay? So I'm going to actually put this on Desmos so that we can see that this is what the graph will look like, but I'm mostly interested in seeing that the range of values is going to be between 0 and a third. So what's ln of t plus 3 and 1 over t minus 5? ln of t plus 3 and 1 over t plus 5. And we said that t was greater than -2, right? So I'm just going to do it all the way up to like a huge number. Okay, not too huge because it's going to go crazy. Okay. And so we can see what's happened here. The result of the graph, the range of it, is this value, I'm presuming is a third. Yep, it's a third and 0. It's in between a third and 0. And you'll also see that the input values for this, the domain, the section of the blue on the x-axis, is just that x is greater than 0. The overall graph was originally y equals 1 over e to the x plus 2. 1 over e to the x plus 2. So if I just get rid of these bits for a second, can you see how the blue graph and the black graph are the same, but the black graph contains some of the extra part of the branch that has been removed? How do you think I would be able to include some of that extra bit of the branch? What was the thing that stopped this extra bit of the branch being included? Yeah, it was the restriction. But we'd have to be careful with the restriction because you actually can't put negative numbers into a logarithm. So this is all like the intricacies of how functions are working here. Okay, so we've got a couple of questions here. I think we'll do them together, especially with the stuff to do with logs. If you want to just attempt them yourself, you can do. So we're going to try and do the Cartesian equation of these ones we've got here. It's very similar to the one we had before. So I'm going to make t the subject of this by raising e to the power of x is t plus 2. So e to the x minus 2 is t. And I can substitute that into y. So it will be e to the power of x minus 2 plus 1. So 1 over e to the x minus 1. This was from 2008. So probably 2 marks now, unfortunately. And so we can do the same for this one. They like doing logarithms here, but you're going to get used to logarithms just by seeing me do logarithms as well. So I'm going to make t the subject of this one. So it will be e to the x equals t. And y is equal to t squared minus 2. So y is e to the x all squared minus 2. What is e to the x squared? E to the power of 2x, okay? If you're not sure what e is literally just a number. It's like pi, okay? So if you're seeing e and you're like, oh my gosh, what is it? It's just a number, so you're just going to follow all the same things that we would have done before. Because the powers are just multiplying, yeah? The powers multiply, so you get e to the 2x minus 2. I think that's what these would have been here. Let's just confirm that's what the mark scheme said. Yes, we've got 1 over e to the x minus 1. And then here we have got e to the 2x minus 2. So we're going to do a few questions from exercise 8A. And I think you are going to try and decide whether you want to be looking at the ones with logs or whether you want to be doing the ones that are just polynomials and stuff, okay?